Hello, everyone. Today I'm going to talk about OMRGx, which is programmable and transparent out-of-core graph partitioning and processing system. So single machine analytics has recently gained popularity, and there are single machine systems like GraphChi, GridGraph, which have been developed. I'm sorry. So there are single machine systems like GraphChi, GridGraph, which have been developed to work on single machine, and they can process large graphs. So the first question is, why do we need single machine systems instead of distributed systems? The main motivation behind using these single machine systems is to avoid the complexity of using distributed systems. Users often need to tune a number of parameters in order to get performance, better performance, and it requires users to be highly skillful. Although distributed computation resources are widely available, developing distributed algorithms still remain challenging to its users. So now the question is, how do these systems perform computation on big data with limited memory? The answer is that they transparently support out-of-core processing, which means that they employ disks to process large graphs. While there are these well-tuned systems which require processing of the input graph in order to partition and process them on a single machine, there is no out-of-core system that provides users with the flexibility to write custom graph partitioner and perform partition-based graph processing. So here we introduce OMRGx. It first uses the available memory to form multiple in-memory buffers that are used by multiple threads to simultaneously create partitions and simultaneously process partitions. A partition doesn't need to fully reside in memory, but it is rather streamed through the memory buffer assigned to the partition. Second, it uses a novel strategy for representing multiple partitions in memory and on disk, while seamlessly moving them between memory and disk, giving the illusion of entire graph being available in memory to the user. So together, these two features, they enable the exploitation of parallelism in computation and I/O, enabling processing of large graphs on a machine with limited memory. OMRGx has a MapReduce-based out-of-core engine, so it also provides programming interface where users can express their partitioning logic using the map API and processing logic using the reduce API. So this picture gives you a higher-level overview of OMRGx. At the base or at the core of the system is the MapReduce-based out-of-core engine. It handles all the messy details like creating mappers, reducers, managing the memory between disk and memory, disk and in-memory. We provide core APIs to the programmer, which help them write different graph partitioning and processing algorithms. At the top, you see graph partitioning and processing algorithms implemented in OMRGx. These are some additional APIs that you can use to program complex graph algorithms, partitioning as well as processing algorithms. The details of those can be found in paper. Here, we consider an example of our programming interface using a PageRank example. So as you can see, we are using a hash class, which has been implemented in OMRGx. So we are using hashing as the partitioning scheme to partition the input, and we are implementing PageRank to process the graph. Programmers, they can specify their custom graph partitioning logic using the setPartition API, setPartitionID API. The map function will partition the input graph based on the custom partitioning logic specified by the user. And at the end of the map phase, each vertex is hashed into one of the partitions. So for PageRank, we specify the edge type to store all the attributes related to a vertex like source, destination, number of neighbors, etc., which are stored along with its key, which is the source ID. And then during the reduce phase, the partitioning processing logic is specified. So all the edges corresponding to each vertex within a partition are merged together by the reducer and made available in the partition. Therefore, for each key, its rank is calculated based on its previous rank, which is stored as its attribute, along with its neighbor edges. It then updates the new rank for all the neighbors of the key. Once the entire partition is processed, the update reduce iteration API, it increments the number of iterations to the page rank algorithm until it finally converges. So here we see the main method. It creates the map and reduce task. We also see the run method, which initiates the engine. On your right, you see the protocol buffer, which we use edge type. So we are, as I mentioned, we are storing the attributes of each vertex, number of neighbors, rank, etc., in this edge type format. And this is when we create the object of this class here, we pass this edge type to the method. So you also see the record type at the end of the protocol buffer. So when we are storing the records on disk, we serialize them as record types and then store them on the disk. Next, we understand how OMRGx organizes the memory into buffers and disk space. So to parallelize the I/O and processing, we use T threads that read from disk in parallel and create the partitions in parallel. To ensure that these threads do not have to synchronize with each other when updating the buffers, each buffer is subdivided into T subbuffers, one for each thread. This leads to the organization of the graph as shown on your left, where the number of in-memory buffers is a number of threads multiplied by number of partitions of the graph to be produced. Corresponding to each of these buffers, the disk contains a series of batches. So once the in-memory buffers, they reach their capacity, their contents are emptied on disk, which are written as batch. So corresponding to each partition, as you see each color, red color, there is one partition which contains series of batches on disk. Let's consider a small toy example here. So here, a key corresponds to a vertex ID, and the edges represented by destination vertex IDs, they correspond to the value. Here we want to create two partitions of the input graph. So during the map phase, each mapper threads, it reads the vertex key along with its value edge type based on its partition ID to an appropriate buffer in its row. We use in-memory, ordered in-memory buffers. So we also perform on-the-fly aggregation of the key. So if the key has multiple values, the values will be aggregated for the same key. Once the in-memory buffer reaches its capacity, its contents are emptied to disk as a batch of contiguous records. The contents within each batch are serialized as record type. So at the end of the map phase, any given key will be present in some or all of the batches within the same partition, and the entire graph is partitioned and stored on disk as shown. So this is the partition 1, and that's the partition 2. During the reduce phase, the engine initiates the reducer threads based on the number of partitions of the graph to be produced. Each reducer thread reads as much from each batch within its assigned partition. It deserializes the record type into its corresponding key value pair, and also merges the value split across batches within the same partition for each key. This in-memory partition is then used to run the user-specified graph processing logic using the reduce API, and it writes out the final partitions on disk. OMRGx has been implemented in C++. The records are expressed using protocol buffers. The graph is represented in memory using adjacency list format, and we use vertex ordered representation of the graph. All the experiments were performed on a single machine. We used input graphs ranging from medium to large size, so from 15.5 million to 3.3 billion edges. The goal of our evaluation was to compare programmability, performance, and scalability of graph partitioning and processing algorithms implemented in OMRGx. So we also performed experiments to show benefits of parallel partitioning and processing. These are the graph partitioning algorithms which we implemented in OMRGx, and below you see the graph processing algorithms. So for graph processing algorithms, we also compared their performance with their standalone implementation. So here you see the programmability. So it took under 200 lines of code to implement complex graph partitioning algorithms like Go and MtMetis. And it is important to note that we came up with the first out-of-core implementation of in-memory, which was in-memory MtMetis partitioner. Graph processing algorithms like GraphChi and GridGraph, we were able to implement them in under 85 lines of code. OMRGx also provides a self-contained system in its default state, which uses hash as its partitioning scheme and PageRank as its processing. And OMRGx, all the heavy lifting was done by the runtime, which is implemented in about 900 lines of code. Next, we see the graph partitioning algorithms. Here we see the sensitivity of the runtime performance of the number of partitions produced. So x-axis shows the number of partitions, which vary from 2 to 32, and y-axis show the time, runtime performance. So here you see the cost of partitioning for all these partitioners is reasonably small, except you see MtMetis as an outlier. So I will let you guys know that MtMetis, it uses a coarsening, coarsening scheme and uncoarsening scheme where it creates multiple copies of the graph, and then it uses the refinement of those partitions using the KL algorithm. So that's the reason it took more time for that. It is also, again, all the other partitioners, they were able to perform reasonably well. Next, we compared the sensitivity runtime performance for graph processing algorithms. So here we see GraphChi, GridGraph, and OMRGx default. And then we compared their performance with their standalone systems as well. So as you can see, these algorithms, GraphChi and GridGraph implemented in OMRGx, it performs far better than their standalone systems. This is because their standalone systems, they work on one partition at a time. They pre-process the graph and bring one partition and then process it using multiple threads. However, OMRGx benefits this from parallel partitioning and parallel processing of the graph, which gives it more advantage over the standalone systems. There are more results, experimental results, which you can find in paper. We also studied the scalability of graph partitioning and processing algorithms. We show the results of parallel processing of the partitions. And we also share how we program complex algorithms using OMRGx. Coming to the conclusion, we presented OMRGx, which is the first MapReduce-based out-of-core system which can process graphs. Users can rapidly prototype a variety of graph partitioning and processing algorithms. Programming can be done oblivious of the relative size of the graph and machine memory. And this is, again, a first system which simultaneously create and simultaneously process all the partitions. We also came up with our first out-of-core implementation of the popular MtMetis partitioner. Thank you very much. Any questions?
All right, any questions?
Thank you. The kinds of algorithms you're looking at suitable for in-memory compute systems?
So the algorithms, it's not about the algorithms, it's about the partitioning of the large graphs. So we write algorithms to process the information from big data or large graphs, right? So these algorithms, they can work for in-memory, but if the size of the graph is large, that's when we need, more algorithms to process that. Is that the question that answers your question?
Maybe. I'll talk to you afterwards.
Sure.
More questions? So you focused on MapReduce. And I guess one of the trends in big data computation over the last couple of years has been to have more and more general like data flow processing frameworks. Do these techniques apply there as well? Or does MapReduce cover pretty much all the important use cases? Or how do you see the relationship between them?
So I chose MapReduce because it provides a very simple programming interface. So that's the main reason. I wanted a system where users can just focus on the processing logic and everything else can be left. So we have MapReduce systems to process key value pairs, but for processing the graphs, I thought we can extend the MapReduce system, and then it has everything. It provides APIs. It didn't support graph processing. We can benefit from that, from the simple interface.
That makes a lot of sense. Thanks.
Can you go to slide 14 to follow up what Jeremy was asking? So are you, for example, partitioning a graph that's probably 1 terabyte in size into pieces that can be processed in memory within hundreds of gigabytes?
So I'll just clarify the question. So you're asking how we are processing very large graph. Are we partitioning it and then using it? The answer is yes, but the partition size is not fixed. So if you look at how we organize the memory, the in-memory buffer size is fixed. We are streaming the partitions from disk and storing them in memory. So as much as we can store, we process those, and once we are done with the processing, we empty those and then bring in the other chunk from the disk.
Okay. Do you have a measure how much slower your system compared to in-memory partitioning?
So I also measured the I/O. It's not, because we are doing parallel processing. We are also bringing chunks from memory. So it kind of hides how much it takes for the I/O time. It doesn't take as much because everything is happening in parallel.
So I think we have time for 1 or 2 more questions. Okay, I'll ask one more. Do you think any of this work is applications to training of graph neural networks? Could this help with training GNNs more efficiently?
So I don't have much knowledge about neural networks, but I know they also form, we can read them as a graph, right? So yes, you would be, if we read the data in the form of graph, yes, you will be able to process them using this system.
Yeah. So graph neural networks in particular are processing graphs themselves. So yeah, it sounds interesting. Thank you.
Yeah, that was a great question.
All right, let's thank the speaker once again.
Thank you.